Namaskar.
Namaskar. Yes, sir.
It is on now. It is live streamed.
Okay, sir. Sir, please
Yeah,
make
okay.
me as the again host. I will reclaim. Yeah. Okay, sir. I reclaimed. Yeah.
So I can start my presentation, sir? Are you doing from
Sir,
your side?
just 1 minute, sir.
We have some formalities to do and
Okay, sir.
welcome you.
Got it.
Okay.
Good afternoon to all, as per the Indian Standard Time. And today we are having the 6th lecture on the Radar Meteorology Lecture Series organized by South Asian Meteorological Association in partnership with the Advanced Center for Atmospheric Radar Research, CUSAT. So today we have an eminent personality with us, Shri Y.K. Reddy from IMD. So before starting, I invite Professor Somesh sir to propose the formal welcome address.
Thank you very much, Dr. Avilas. Good afternoon, everybody. President of SAMA ABM, Professor Ajit Tagi Saab, the chairman of the advisory panel of this lecture series, Dr. Divind Pradhan Saab, today's distinguished speaker, Dr. Y.K. Reddy Saab, our advisory panel member, Dr. Kyalvin Wu, and the nominee from Bangladesh, Mr. Salam, all the members of the organizing committee, ladies and gentlemen, and of course the participants. We welcome you on behalf of the South Asian Meteorological Association and the Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology for this 6th lecture of the 20 weeks lecture series on radar meteorology. As you know, now we have closed the new registrations because more than 25% of the lectures are over by now. And the last registration about 1105 or even more than that people registered from about countries for this course. And I just checked also the YouTube channel. We are getting very good hits for the lectures. I think the first lecture was viewed by more than 800 people. And it's also increasing slowly. So the lecture series is becoming very popular. And since all the people have already registered and know the rules, so I do not have to repeat the rules now. So without taking much time, I welcome once again everybody and wish you all the best for this today's lecture. Thank you very much. Over to you, Dr. Avilas.
Thank you, sir. Now I request ABM Professor Ajit Tyagi sir to propose the presidential address. Sir, please.
Thank you, Abhilash, and I join Somesh and you to welcome all our distinguished participants and, of course, today's distinguished speaker, Dr. Y.K. Reddy, Dr. Pradhan, who has been leading this program, and also our organizing committee members. Of course, we are happy to have our colleagues from Myanmar and Bangladesh in today's lecture. I'm really happy and thankful to my senior colleagues from the IMD who have agreed to deliver this lecture. And after starting with the basics, now we are at the stage where real application, operational application, we are going to cover in today's lecture. We started with the basics, 2 lectures from Dr. Pradhan, then we had a lecture from our friend Kannan and followed by Gajendra Kumar. So the basics are now covered and we are now moving into the applications, and today's is going to be the most important aspect of the application of radars in cyclone monitoring and short range prediction. So this is the critical application where all the features which were theoretically covered will be demonstrated and covered by the Dr. Reddy. So I request all the participants to I think it will be very interesting, but make best use of it while attending the classes, and also thereafter in the question and answer session also you can put up your doubts, and of course it will be available on the YouTube. So keep benefiting and keep in touch with our core people who got still some doubts left. We will try to put you to our experts. So this is a platform where we would like young researchers, students, and operational people to benefit from the experience of our senior eminent speakers. So in this series, once again, I thank Dr. Reddy to have agreed to deliver this particular lecture, which is so important and relevant. Thank you.
Thank you, sir. Before moving to the lecture, I invite Dr. Paulomi to introduce today's speaker.
Very good afternoon to all of you, and with the permission from the host, may I share my screen? Yeah, thank you. So in today's lecture, we are honored to welcome Shri Y.K. Reddy, who is the Scientist F and is the retired Deputy Director General Admin from India Meteorological Department. Shri Y. Karunakar Reddy.
Screen is not shared.
I'm sorry, am I not audible?
Please continue. Please continue.
Shri Y. Karunakar Reddy, sir, is an accomplished electronics and telecommunication engineer who boasts a remarkable career that includes 12 years of service in the Indian Air Force, specializing in airborne radio communications. With a nearly 30 years of dedicated service at the India Meteorological Department, Shri Reddy has held various prestigious roles such as Head of Doppler Weather Radar, stationed in Machilipatnam, Head of Meteorological Center in Hyderabad, and Deputy Director General position at the administration at IMD headquarters in New Delhi. And I cannot go to the next slide. Yes, Shri, can you see the next slide? Yes, Shri Reddy sir has vast experience in the installation, operation, and maintenance of advanced meteorological instruments, including Doppler weather radar systems and automated weather stations, contributing significantly to the field of weather forecasting and services. His area of expertise include surface meteorological observation system, which I discussed earlier.
Shri Reddy sir has vast experience
such as manual observation and automated weather stations, as well as upper air meteorological observation systems like radio sonde and pilot balloon systems. Retiring as Scientist F in September 2021, Shri Reddy sir's career is marked by his leadership and expertise, and he currently resides in Hyderabad, India. Sama, jointly with ACARR CUSAT, is honored to welcome Shri Y. Karunakar Reddy sir to this online session of the Radar Meteorological Lecture Series. So we welcome you all, sir.
Reddy sir, please.
Can I go ahead, sir?
Yes, sir. Please.
Thank you, Dr. Paulomi, for your nice introduction. And thanks to Dr. Aditya Saab and Dr. Someshadar Saab and Pradhan Saab and Abhilash Saab and all those dignitaries who are organizing this SAMA's radar course for international audience. In fact, this is a very good initiative by SAMA. I think this is the second such one after the satellite meteorological course, which was completed a few months ago. This is going to definitely improve the knowledge of the people, especially the meteorologists who are interested in learning these about Doppler weather radar or even other radars like dual pole radars and even the they can say the forecaster technology developments that are going to happen in this field. So with this, I would like to start my topic of the day, that is monitoring of cyclones using Doppler Weather Radar. Yeah. So having the experience at Doppler Weather Station, Machilipatnam, exclusively for 5 years, where I had the opportunity to track certain some cyclones like Ogni in 2006, and another 10 years experience at Hyderabad Doppler Weather Station, which was of course not in tracking the Doppler cyclones, but in thunderstorm, hailstorms, like severe weather phenomena using Doppler Weather Radar. So I would like to talk to you in a free way. If you would like to put some questions, you can interrupt me anytime, and we can discuss a bit. As far as possible, I will try to clear. Otherwise, I have my Guruji, Dr. Pradhan Saab, who can also help me in clearing the doubts of the audience if I am not able to answer. Yeah. So, as you know, the DWR is a very, very sophisticated electronic equipment.
Sir, one minute, sir.
Yeah.
Do you want me to share the PPT from our side, or you are sharing?
I think you can share, sir. It will be free for me. Maybe some
Okay.
issue in screen sharing can happen sometimes.
Yeah.
So the main presentation he can play. So I think you can full screen, make
Yeah.
it full screen.
It is full screen. അറിയില്ല. പ്രമേയം സ്ലോ ആണ്, സ്ക്രീൻ 2 ആണ്.
Yeah, I think this is the first slide is only the name. This one is the topic actually. So as I was saying, cyclones are monitored as a duty. IMD has the very, very important function of monitoring cyclones, and various means and technologies are used in such a function. Like we have satellites which actually detect the cyclones right from the genesis stage, which are much normally away from the coast where the radars are installed. And we have Doppler weather radars installed at the coastal places and sometimes islands also, which can detect and track the cyclones if they are within 500 kilometers of its radius. And then we have the predicting systems like NWP, where genesis is predicted much in advance, and that gives a initial trigger for a meteorologist to look at these satellite images, and if there are radars nearby to that images, so that we do not miss even a small severe weather system like cyclone. So as you see the cyclone from a satellite, it looks like this. So you have a central cloud-free area, which is black here. And then that is called the eye of the cyclone. And it is surrounded by very strong and tall clouds. That is called the eye wall. And surrounded by that are very larger spiral bands. The spiral bands are again having very tall and convective thunderstorms or hailstorms cells embedded in the spiral bands, and they revolve around the center, that is the eye, continuously. Next slide. So when you look at such a cyclonic storm from weather radar, Doppler weather radar, it looks like this. So this is a max Z velocity. Sorry. Hello.
We can hear you.
You can hear, but my screen has gone. Maybe there was a call, so that disturbed it. 1 second. Yeah, so I got it back. So I think you need to go backwards slide. Yeah, this one. So this is a max Z image. That is the picture which shows us the maximum velocity as seen from ground level to the top of the atmosphere. Generally, we use this Doppler radar to scan the atmosphere in different elevation angles so that it constitutes a volume of the data. That volume is generally from 0 degrees to around 15 kilometers. It can be rather it can be configured to scan even up to 20 kilometers or so if required. So as a practice, we are doing it up to 15 kilometers because all these storms that are there will be up to that height only. So yeah, so you can see here a circular portion on the south side. I think my mouse, are you able to see my mouse position, sir?
No, sir.
No.
Screen is shared by Dr. Avilas, so we can't see the mouse on your screen.
Mouse, you can't see. Okay. Right. So if I share it, I think you will be able to see.
Yeah.
So anyway, so I'll try to speak that. Yeah. So so little more to the left. So that is the eye of the cyclone here, and there are closed spiral, which are called even eye valves. And to this is detected by the Doppler Weather Radar Station Machilipatnam, where MPT is written with the center of the figure. Okay. So on the top side, on the left side, there are height panels which depict the heights of the clouds. So generally, the eye wall clouds are taller than the surrounding clouds. And you can see the intensity is shown in terms of the colors. The blue, dark blue is the very lowest intensity, and the red is the very highest intensity, in this case, up to 65 dBz. So white is the middle value, you can say. So the lowest color starts from dark blue and lightens its color towards white as the intensity increases, and then starts into yellows and oranges and reds as the intensity further increases. So in this, we are able to see only yellow color. Maximum reflectivity I can see is about 50 dBz around. Okay, so next. So this is another case of a cyclone as seen in the Doppler Weather Radar, which is detected by the Kolkata radar. So in the middle of the circular image is the Kolkata, and to the south of it, around 150 kilometers or 140 kilometers, you have a hole without clouds, and that is the eye of the cyclone. Yeah, so you can see the radial rings. On the bottom, you can see 200. That is the 200 kilometers. The outer black color ring shows the 250 kilometers radius from the Kolkata radar, which is the scan range of that radar used in this particular case. Radar can be used to scan up to 600 kilometers. So when you configure the scan schedule like that, the timings as well as the ranges which we define are included in the images in the data. Yeah. So next. So IMD has installed these Doppler weather radars along the east coast and west coast, more number in the east coast because Bay of Bengal is more prone to cyclones than the Arabian Sea relatively. Therefore, the initial radars in IMD were used for cyclone detection only. They were installed on the coast. Not only the Doppler radars, before that, the conventional radars, which were installed in right from 1980s, they were on the east coast only. The first Doppler weather radar came in India at Chennai. So followed by the Kolkata and followed by Machilipatnam and then Vishakhapatnam. And further, we got more radars for coastal stations as well as the interior stations. So IMD always keeps watch of these cyclones entering into the scan range of these radars, which is about 500 to 600 kilometers. Normally 500, but can be used up to 600 kilometers. The next slide. So when you see the structure of a cyclone in the satellite image as well as the radar, we have seen a cloudless region or a hollow region. that is called the eye. And theoretically, the structure is like this. It will have a eye. I think I should switch off my phone so that it is disturbing. Sorry for the disturbance. So can you go to previous slide? Yeah, so the eye. So when you say eye, it has certain parameters to be looked at. That is this is actually the central portion of the storm, and it happens in the lowest pressure area. It will have the less clouds or no clouds or even weak winds. Okay, then eye wall. It will have a narrow, about 10 kilometers or 15 kilometers thick eye cloud walls. It is a circular wall of thunderstorms surrounding the eye, and spiral bands, which are spreading even up to hundreds and thousands of kilometers away from the bands. Next slide. So this shows the vertical cross-section of a cyclonic storm. This is basically a theoretical one. So you can see again the eye in the middle and the eye wall on both sides. In the eye region, the winds are flowing into the cyclone from all around and move vertically up in a spiraling fashion and make an outflow at about 10 or 15 kilometers, depending on the intensity of the storm. That is outflow of these clouds. Okay. So the spiral bands are much away from the center and immediately surrounding the eye are the eye wall clouds. Next, sir. So we have more images to understand the structure of the cyclones. So one more, this figure was, I think, probably made by Dr. Raghavan. He is another stalwart in the field of meteorology and especially radar meteorology. So he has made this black and white picture using his own probably sketch pen. So here also you will see the eye in the center and eye wall around, followed by the spiral bands. Okay. Sometimes you have double eye. So one closed, you can say, wall of clouds, thick clouds, and a little gap around it, and again another round of very tall clouds, thick clouds. Sometimes these are called two eye walls. So this is double eye cyclone. It is referred to. This also happens sometimes. So we have recorded in India by some radars earlier. We have some pictures which I will show. Next. Yeah. So these spiral bands are already having certain relationship with the center of the cyclone. So in olden days, when these Doppler radars were not there, in the conventional radars, where we could to see the intensity of these echoes in white colors on a black monitor, and we used to have a slide-like thing overlay, which has these spiral bands drawn on it using this formula, R is equal to AE to the power theta tan alpha. So you can make a spiral band, which is also called like a conical shaped spirals. So this we keep in alignment with this real cloud pattern and then try to fix the center. I think I'll explain more in the coming slides. Next.
Yes.
So this is the eye of the cyclone. You can see on the left image, there is a cyclone. The radar is onto the north of this image. In both the cases, the cyclone is to the south or southeast side in the left image. So because of the rotation, because the cyclone is basically a rotational system. So we have a lot of wind blowing into the center of the storm, and which pulls the clouds also into the center. And while it is rotating with high speed in the middle, they try to reduce their angle of the spiral, and they become a circular in shape, and that's what we see as a eye. So that's what you can see in this, and the spiral band you can see right from the northwest direction, the white patch of clouds in that shape up to the center. That is just the cloud band where you are showing very nearer to the radar. The radar center is on the top. The here, the right, a little more northeast. From northeast, you can draw along this white band and come to the center of the storm. The center of the storm is some more south. Unfortunately, you can't see this. Yeah, okay. That is actually the cyclonic storm, and the eye is there. From there, you have to go along this band of white clouds, outer band, and goes to the northeast side. So that is a spiral shape. So when you don't have a clear digital image processing, the conventional overlays of slide with different angles of the spirals, 10 degrees, 15 degrees, 5 degrees, like that, we used to make the slides and put over the monitor and see, match this cloud pattern with the spiral bands, the outer area of the spiral bands, and we get the center fixed that way. Anyway, next image. Yeah, okay. This is the eye wall. So eye wall you have seen in the previous image. It is basically surrounding the eye and with a tall clouds. How do you see the height of the clouds, the tallness in the clouds? So if you see in this image here, on the left, where you have the white vertices, they are the center of the radar, basically. That is the radar location to the left. Okay. So yeah, so moving to the right, yeah, there is the eye. So both sides of the eye you are having tall clouds. So those that is a vertical section of the clouds of the eye wall. So before that, up to the radar, there are thunderstorm clouds which are part of the spiral bands, or sometimes may not be part of the spiral band, but isolated thunderstorm clouds and all those things which are in that direction. What we do, we normally radar continuously rotates at certain speed horizontally. And when you find in one direction a cyclone, example, let us say it is on the north side of the radar station. So when the antenna goes to the north direction, and the cyclone, the radar beam is passing through the cyclone, and we stop the horizontal movement there, and we play the elevation angle up and down. Then we get this vertical section of the clouds, the inner side of the eye wall and outer side of the eye wall, and any further cloud bands away from the center. The further part of the cyclone also can be seen, but mostly these core eye wall clouds are very strong, and they absorb the radio frequency energy, and definitely the radar beam weakens over there, rather gets attenuated. And even though there are very strong clouds on the other side of the eye, which are far away from the radar, so they may not be rather detected by the radar because of the weakness in the signal and travel to and fro travel of the radio waves from radar to that cloud and back. So that's what. So the in vertical cross section, it looks like this. Okay. Next. This is the double eye wall cycle. You can see there is a black hole-like thing in the middle, which is around surrounded by one eye wall. And again, there is a black circular area that is called again a second eye-like thing. And surrounded by that outer side is the second eye wall. So this was the cyclone recorded in India. I think this is by Visakhapatnam radar. I have not mentioned, maybe in another image it may be there. Next. The same image which you have seen here in the vertical cross section using the conventional radar. Yeah, here it is written Machilipatnam radar, Southern Visakhapatnam. It was recorded on 9th May 1990 at 00 UTC. This type of scan is called RHI, that is range height indicator. So you can also see the height of the cloud. Previous slide, please. The height of the cloud, maximum height is 8 kilometers. So it is not very severe going by this height, and generally the intensity of a cyclone storm is read by the height of the cloud also, height of the eye wall clouds especially. Next. Then further details of this cyclone parameters include this. For eye, you need to have location, where it is located, what is the latitude, or by range azimuth to a particular radar, which direction and how much distance it is located. Then the diameter of the eye. how much is the total cloud-free zone. Then the shape, whether it is a circular or elliptical, or it is a partial ellipse or a partial circular, or could be there another similar nearby matching shapes available to that cyclone. And then a type of eye, that is single eye, double eye, what we have seen just now. So this can be seen. And eye wall, when we talk about eye wall, we will think how much is the width of the eye wall on all around the eye. So then what is the height of the eye wall cloud, and what is the maximum reflectivity and its altitude in the eye wall. So maximum reflectivity nowadays in the Doppler Weather Radar, you get it by in the max Z reflectivity image. How much it is, a 55 dBz or 60 dBz, something like that, it would be there. And it may not be at lowest level, that it may not be close to ground. The highest reflectivity could be somewhere above the ground level, could be at 3 kilometers height, 4 kilometers height, depending on this storm. So we need to find out where it is actually the highest intensity. And then the velocity wise also, what is the maximum velocity in the eye wall? What is the maximum radial velocity, and what is its altitude? It is showing the maximum velocity. And spiral bands, how many spiral bands are seen? So in normally to measure the center accurately, we need to have at least 2 to 3 spiral bands. So larger systems do have more, 5 to 6 spiral bands, and smaller systems may have 2 to 3. So single spiral band is very rare, but it is sometimes embedded in the nearby clouds. But we need to check the spiral band shape and location by filtering out the low intensity clouds. You only look at the high intensity clouds more than 35-40 dBz, then you will find a pattern, and that is actually the spiral band pattern. And once doing this, then by seeing the animation or hourly or 3 hourly locations, we can find out what is the speed and direction of movement of this storm, total storm. Not a particular wind there, not particular reflectivity, but the whole system, cyclonic system, how it is moving, we can find out in terms of kilometers per hour for speed and compass direction or latitude, longitude of the location. Next, sir. So when we are going to see these images and analyze it, I thought a little bit revision like thing I will do on the velocity measurement, how you identify the velocity values and reflectivity values from an image. So next. So these are the important images we are going to use in monitoring of the cyclones. So the first left, top left one is the reflectivity image, PPI, plan position indication reflectivity. It is having a range of 250 kilometers around the radar. So as usual, you find the reflectivity values of the clouds, or rather the intensity of the clouds, how much rainfall we can expect at various locations in this radar area. You can see. So as you know, the red is the strongest part. You can see here where the marker is being shown. The right part of this, left part of this eye wall is stronger than the right part. Okay, this is the reflectivity, not the velocity, mind you. So the strong, sometimes the eye wall is not uniformly having the same intensity. One part of it may be very bright or very strong in intensity, other part may be weaker and with lesser altitude as well. Okay, so you can see the spiral band coming from the south, directly almost close to Chennai, I think, Ongol. So it's moving from the south towards the east and then to the cyclone center. There's a cyclone, you can say the spiral band. That is the outer one. Next is the velocity here, right one. Sorry, same slide. So next to that image, this is the PPI velocity. This is the plan position indicator having a range of 250 kilometers. The outer circular black ring is the 250 kilometers one. So in this, the middle part is center of this image is the Chennai. radar station. And to the north of it, you are seeing a blue and red color pair of these values there. So that is the center of the storm. Blue is the area which is shown by the velocities which are moving towards the radar, and red is the area where the velocity is moving away from the radar radially. So that is why the color code shows there. The blue colors here, the color code is legend is same as in the reflectivity, but the meaning is different here. The blue colors represent the radially towards radar winds, and yellow and reds show the velocities away from the radar. Okay, and the blue, the darkest blue color shows here minus 45 minutes, minus 32, I think 39 meters per second wind speed. The topmost color, red one, shows 26 to 30 meters per second. So this is the velocity. I will explain a little more in the next picture. And the left bottom is the max display reflectivity. It is almost similar to the top one, plan position Z, but has the difference of additional height indicator panels on the top as well as on the right, which show each cloud is extending up to what height in the elevation scale or in the altitude scale. So here we can see by this image, the dark colors are up to, we can say the white, which is about 25 to 35 dBz, is around about 8 kilometers altitude. Below that, the strength of the clouds is more, and above that, the clouds are weaker. We can understand that by seeing the top part or the right part of the image. And the next to that max V image, if you see, similar to the PPV image on the top, but here again the additional panels are there for measuring the heights where these high winds are located. We can find out. So you can see these the red and blue patches. They are not actually close to the surface, but at certain height. Yeah, so somewhat about 4 kilometers height or so, the intensity or velocity is more there. And the rightmost image is the velocity VVP2 or volume velocity processing 2. It is best a name given to the kind of processing they do. So this image is a time profile, vertical profile of the horizontal winds. So if you see, there are vertical lines there in the image. The legend shows 0 kilometer at the bottom, and the top is showing as how much it is. It's very small. I think at 4 kilometers. Every 300 meters, the horizontal wind is marked. The rightmost image, rightmost image, rightmost image. Still right. Rightmost image, volume velocity processing 2. Yeah, this one. So this image, the left, the legend is the height, 0 kilometers, and then 0.1 kilometer, 0.2 kilometer, 0.3 kilometers. So every 100 meters, the values are shown, sir. The values are actually showing the wind barbs. Wind barbs are, you can say, an image which depicts the direction and speed of the wind. So wind barb, maybe most of you must be already aware. And as you see in this image, the first immediately after the height scale, you see, I think 139 is the image. So at that time, the winds at the radar station were like this. At the bottom, I can say at lower levels, the winds were easterly, about 10 to 15 knots. At higher levels, also almost same. If you see the rightmost line, vertical line, the timestamp here is showing around, is it 9 GMT? I think so. So there, in the lower levels, the winds are easterly about 5 knots. And on the upper levels, the winds are up to 20 knots. You can say around 3 kilometers height, about 20 knots wind is there again from easterly direction. So wind speed variation is there from lower level to higher level in the east one. In this one, the winds are recorded at the radar station around 30 to 60 kilometers around this thing only. It doesn't actually mean the velocities in the storm. They only mean the velocities at the station. Yeah, next. So again, some more detail. I have just tried to show the legend of the color values into the image. So again, there is one right side image shows red and blue color, red, yellow color and blue color, light blue color areas. So here also that there is a cyclone is there. We can say that because this is cyclone because when two colors are there adjacent to the means two colors means red color is the winds that are away moving away from the radar. Away means radially away, and the blue color ones the winds that are moving radially towards the radar. So if they're just a little by nearby, if they are moving like that, it means there is a rotational pattern over there. The winds are moving in a circular pattern at that location. So going by the intensity values here, I have given 1 in the image. You see the green color dot. So that refers to white color there. So in the legend, white color means -3 to 3.3 to plus 3.3. Means the wind speeds are varying between -3.3 means either away from the towards the radar at that 3.3 meters per second maximum, can be 0 also, or can be away from the station at 3.3 meters per second. So coming to the number 2, this is a light blue color. It is showing a winds of -16.7 to -10. Rather, I should say -10 to -16.7. Minus actually means it's towards the radar. It only means the direction, that is towards. So you can leave the value of the sign, negative sign, but you can take the wind speed as 10 to 16.7 meters per second, but radially towards the radar. The next one, 3 shows little darker color, blue one. There it shows 16.7 to 23.7 towards the radar. So the velocity is increasing. So number 4 is showing -23 to 30. So similarly, the 7, the highest value observed in this image, where the 7 is mentioned, is showing a value of -36.7 to 43.3. So that is in the eye wall of the cyclone. And this one is towards the radar. So here the winds are moving towards the Machilipatnam radar radially. So the highest winds in this storm, we can say, are 36 to 43.3 towards the radar. And they, but how do you say what is the correct value? So this is one disadvantage here. We are using a range of values in the legend, and the data recorded actually is shown in terms of the range only. But really, if you sit on the live display of the radar system, if you put a mouse pointer at that point, it will show the exact value, not the range value. In the image purpose, we are only selecting certain ranges because we cannot have infinite number of colors here. It will be very difficult to distinguish and a lot of confusion would happen. So ranges are used here. So even if you go by this image value, so since it is 36.7 to 43.3, the mean middle value, if you take it, is 40 meters per second, which corresponds to about 144 kilometers per hour. Sorry, it is not miles per hour, it is kilometers per hour. It is a mistake. Yeah. So that way you can look at this velocity image and identify the velocities at different places within the storm region. Next. Similarly, same color code can be used as per color, how to in the reflectivity also. So if there is a reflectivity value white, it will have some value. It is not again middle value. It is intensity scale is actually starting from normally 20 dBz to about 60-65 dBz. So the white there would show some maybe 30 to 40 dBz like that. So this is one example of a folding velocity where while making the scan strategy or scan parameters, you have used very low PRF, or you have set it for the range calculation, and you are using it for, you are generating a velocity image from that. So in that case, because the radar system is not capable of measuring high winds above a certain value, which is defined by the PRF set, going by that equation, so you will get the velocity folded, because in the actual system, cyclonic storm, the velocity is, say, more than 25 meters per second, but the data while scanning has not considered that, and you have set it, see, maximum velocity is 15 meters per second only. So therefore, the velocities above 15 meters per second get folded with the other side colors, that the positive colors, negative colors, what we say, they are overlapped by that. So this type of confusing picture you will get it if the velocity folding happens. There is a way you can unfold it manually also, because if you see this legend here, minus 15, 13 to 15 is the darkest blue color showing, and the darkest red is showing 13 to 15. That is away from the radar, radially. So if the velocity toward the radar is showing, in this case, you can say north side, very close to the center of the radar, you have the blue color, but it going from light blue to dark blue, and then again immediately going to red color. So actually, red color means it should have been the next value in the blue scale only. It should have been the difference here is 13 to 15, 2 MPS. So if you interpret the next red value, it will be minus 15 to 17, and then minus 17 to 19. Like that, each folded color can be unfolded. Maybe this was explained earlier to you in the previous thing, but I thought I'll just revise it. Next one. So the same image, if you see the timestamp there, go back and see the radar and as well as the date timestamp. So the radar is this is Chennai radar, 14/12/2003 at 19:13 GMT. Next slide. This is the same village, same data, 14/12/2003, 19:04. I think 10 minutes difference is there in the time, same radar. So actually the same data, here it is unfolded. Here it unfolded, and immediately 10 minutes later, after they realize that there is a folding happening, you change the scan configuration and then increase the unambiguous velocity to 30 meters per second. So in this case, that folding doesn't happen. So you will find in this, you are seeing the north side blue colors, means wind is coming from the north and going to the south. So since southward it is outgoing, then it is represented by the yellowish and reddish colors. So the unfolding can be done by making a scan with increased PRF, or you can say dual PRF. Dual PRF actually multiplies the unambiguous velocity by depending on the ratio of these two PRFs, 500 by 375. If the ratio is say 4/5, you get unfolding 4 times more than the previous unambiguous value. Next. This is another example in a cyclonic storm, how the folding happening this area. So had the radar been set for higher velocity capability, so here they have used PRF 600 by 450. Okay, so you can see in the legend PRF mentioned 600 by 450. So it comes by, I think, 5/4, 4/3. 4/3 is the ratio. So it is multiplying by 4 times. But if you put same 500 by 375, where the unfolding ratio becomes instead of 3/4, it will be 4/5. Then you will get these unfolding happening in the image translation. Next. So this is a normal velocity pattern seen in a cyclonic storm because of the rotational wind. So the left side part is showing a theoretical concept of how the rotation happens. When the radar is on this south, that marking is the radar. So when the winds are blowing towards it is a circulating. So this is an anti-clockwise circulation. Anti-clockwise circulation happens in northern hemisphere in terms of tropical cyclones, whereas in the southern hemisphere it will be the reverse direction, clockwise. So since it is an anti-clockwise direction, the left side is towards the radar, right side is away from the radar. Therefore, this is the theoretical and the right side real image data of the Chennai radar, where the cyclone is to the north of the radar station. You will find. Next. So coming to the fixing the center. So I found by my experience and many more found that the best image, best data of the Doppler weather radar to fix the center more accurately is VPPV image. This is the one. So here you see near the ONG, there is a cyclonic storm rotation happening there in the left image. And the right image, I have just zoomed it out. So you, in the red area also, you will find the darkest red area, one spot, or maybe little wider spot. And in the blue area also, you will find one darkest color one. So take that 2 points and join them by a straight line, and the center of these two locations. So you put a marker in the middle of these 2 points, you get actually the center of the storm. So you in a real working system, if you are on the radar display system, you can put a mouse over there, you will get the latitude longitude value also. Okay. So otherwise, you can note down the latitude longitude and make the center point of it to fix the center. So this is one. You can also use it using the reflective image. I will show you next. Let's next image. So this is a max velocity image. Yeah, in this on I'm not able to see in the slide. I think the bottom part of it. So there is a circular rotational velocity. So you can see a hollow area. That is the center of this. It's not very clear image. Maybe I did not find a good image to show you. This is the Kolkata radar's image. Okay, next. This is VVP2 image where the horizontal wind at different levels near the radar is there. This is more useful for the cyclone analysis when the storm is at the radar itself, very close to the radar, say within 30 kilometers of the radar. If the storm is there, you can use this very effectively to find out the wind speeds at different levels. Also, because this image shows the various timelines. You can see the leftmost column is 305 GMT, the rightmost is 905 GMT, spread across 6 hours. Okay, and every 15 minutes, one vertical line is there. So every 15 minutes, the data is updated. So after another 10 minutes, a new line, the left one goes out and the right, a new vertical profile gets added. So with this, you can come to know what time the strongest winds were there. If you see this image, the red ones where the topmost layer of 7.5 kilometer red is there, you see, that is at 635 GMT. So that is the highest vertical extent of the clouds were noted. And the system is still moving. It has not crossed the station, because once it crosses the station, the direction will change. Next image. Yeah, just to keep you in mind that the height of this radar beam at a distance from the radar varies. It changes because of the earth curvature. This diagram shows what should be the beam height at different kilometers, 200 kilometers, 100 kilometers. So I have given in the bottom text, if you see, normally in India, we are scanning at a lowest elevation of 0.2 degree, almost all the radars, except some variations are there. If you want to do some research and all, they can vary. Otherwise, the scan strategies are fixed. So they are scanning from 0.2 degree and to 21 degree, highest one, with some space in between. Total 10 elevation angles are used to make the volume data. So this volume data, when you see the bottommost beam height for this 0.2 degree elevation scan, would be at 100 kilometers, nearly 1 kilometer, nearly 9.95 actually. and at 250 kilometer distance, it is up to 4.5 kilometers. Means the radar beam at 250 kilometers distance from the radar cannot see any cloud below 4.5 kilometers. There may be a cloud, there may be a rain, but the radar cannot see that. So that is the basic limitation of the radar. So we can find out the values of reflectivity or velocity above that only, and top height is not a problem. So by varying the elevation angles, you can go up to any degree. Generally, troposphere is at 18 kilometers height, so the maximum height of the clouds is that much only. You can find up to that. So this limitation, just to keep it in your mind, I have shown you here. Next. So using reflectivity image, max Z image, how you can get the center, you can see here. So generally you will find a cloud-free zone in the middle and surrounded by very high reflective circular ring-like thing. So that is the eye wall. And you can see many more curved bands of radars, curved bands of high reflectivity echoes. They are the spiral bands. They are not in the circular shape. The nearer to the eye only gets into circular shape. Remaining ones have certain angle. They are called the spiral bands, as you know. Okay. So in this you can see there is one spiral band close to the radar SHH where it is written. That is the lowest spiral, and next to that, right, is one more spiral band. Yeah, come to the right. Come to the right. Right. Yeah, you can see some of them, the bottom where KKL is written, Karaikal. The bottom of the image, KKL is written. Left side. Yeah, so here, yeah, from there, go towards right and take a curve onto the to the center of that one. Yeah, so that is a spiral, the largest outer band, you can say. So where the clouds are very, very tall and very, very intense as well. So from this, how much intensity you can see? I am seeing the highest color of 46 to 6.57 to 50 dBz. And they are at what height? They are not at ground. They are right from ground up to 4 kilometers height. The strongest clouds are there. So the vertical panel, if you see, the every 2 kilometers there is a line, horizontal line on the top one. 4 kilometers, even up to 5 kilometers, the strongest clouds are there. All in the spiral bands as well as the eye wall. Okay, next step. So here we have seen the velocity, how much it was. The velocity is in the previous image we have seen, it was, I think, 30 MPS it was there. And if you see the elevation angle, this is the PPV, plan position velocity, and elevation angle is 0.2 degree. So with this elevation angle, and the cyclone center is at nearly 100 kilometers. So the beam height at that distance is around 1 kilometer. So below 1 kilometer, we are not able to measure using the Doppler radar. Above that only, the Doppler radar will give you the position as well as intensities of various values. So this is one disadvantage. But when we report in a cyclonic report, cyclone storm report, we'll have to say the ground level location, not the location at 1 kilometer. So the cyclone eye wall sometimes is not vertical. It may be tilted in one direction. Generally, it gets tilted in southwest direction. So as per the tilting, if it is at 1 kilometer you are seeing, it may show you slightly towards southwest direction, but the real ground level center may be slightly to the northeast direction. How much that is, it has to be decided by experience and as climatological values of this thing. And maybe some more research is required in this to translate that height at values at that height to the ground level. Next. So this is another case of Chennai radar. showing the max Z image. Here also the velocity you have seen in the previous image, and here reflectivity you are seeing. It is also, even though it is a PPV at 0.2 degree elevation, the minimum, the height is shown above 1 kilometer only. Next. Another example of the PPV image, how to fix the center. Generally, in the middle, there will be white color, but due to in the legend itself, you see there is no white. They have straight away jumped the scales. Actually, this all depends on the scanning. When you scan and set these color codes, if you select 0 meters per second as the white, it will be easy to measure the from the colors this one. Otherwise, of course, in the radar system, when we are reporting, you see with the help of mouse. Next. So here I'm just summarizing this, how you can use this reflectivity, velocity, and max reflectivity images to find the image, find the center of the storm. So in different ways, you can see the same dated images, these all of the thing. And the center as fixed here is 15.1 degree latitude and 80.3 degrees latitude, longitude, sorry. Next. Yeah, this is one case how you can use the VVP2 image to see the crossing of the cyclone onto the coast or onto the radar station. So this is a Chennai radar station where the cyclone storm has actually crossed over the station. So you can see here the PPV on the leftmost, 1341, shows the low-level winds in the northeasterly direction, and the top level is about southeasterly direction. And in about 1734, so there is a change of the winds. When the system has crossed, there is a reversal of winds. So from the lower level, if you see from the east, they have become westerly or northwesterly because it is moving slightly maybe to the not really north, going to the northwest side. Therefore, you get northwesterly wind. So you can see what time that system has crossed. You can clearly indicate in your storm report by using this image. Next. This is another cyclone, is a Phylline cyclone, one of the super cyclones that crossed Odisha in 2013, October. So this is Vishakhapatnam radar, which tracked it. And you can see on the northeast side near Gopalpur, GPL, you have a whole cloud-free zone. That is the cyclonic storm center. That is the eye of this. And between that and the radar station, you are finding the white curved cloud patterns. They are the spiral bands associated with that system. So in this, you can see the upper height pane and the right side hairpin. The red color ones are starting not from the ground. They are at a height. Here, the height scale is, I think, 2 kilometers because the cyclonic storm from the Vishakhapatnam is at about 220 kilometers nearly, and almost at the border, 250 kilometers, maybe 230 kilometers distance it is there. So therefore, the bottom of this radar beam is at a height. And I think this is 4.5 kilometers, the bottom line in the height range. I'm not seeing 0.1. The topmost is 18 kilometers. The white line is 18 kilometers. It means middle one is 9 kilometers. This one 4.5 kilometers. So the below that, the blue, what you are seeing below that thick, or I can say the orange color clouds in the height pane. Below that level, what you are seeing are from different clouds in the same direction. So it's not from the eye, it is from the different clouds in the direction, which are closer to the radar or same distance. Next. So ultimately, after we have tracked the cyclone, and every hourly or 3 hourly, we locate the storm center, and then its parameters, what is the maximum reflectivity, what is the maximum velocity, what is the height of the beam at that level. All those things we put on a map, and we can see the position of the tropical cyclone at various times. So that actually gives the track as observed by the radar. Slight variation may be there when they compare with satellite imageries and other synoptic features. They may correct it a bit. Generally, after the season is over, a big committee sits in IMD and they finalize these tracks very accurately considering the other parameters. Next. This is another cyclone track of the same system. Sorry, this is a different storm in the Bay of Bengal, tracked by the Chennai radar using the same techniques. Next. Next. You have a video showing this animation must be there. Would you like to play the animation, Mr. Rakesh? So you can see this animation, the same Ogni cyclone, which is moving from south to north. Once more, you can do that. So this is the cloud patches before the cyclone, and now the eye is moving from south to north. So it was moving all along the coast, right from Shar, Nellore district to nearer to Bapatla and the east coast. You can play once more, sir. You can see how the spiral bands are rotating anti-clockwise. Once more, you can place.
So you need one more time?
I think that's okay, sir. So I think presentation is almost end. Can go to the presentation, sir. Let me see.
Okay.
Just was doing, I think one thing, see, although we say the radar is very sophisticated and accurate in measuring the various parameters, there are certain limitations of the radar. Like, as we said, the beam height, because of earth curvature, is not always parallel to the ground. So that limits it. We have to keep that in mind. So close to the radar station, we can get the cloud positions or information close to ground, but far away, more than 200 to 50 kilometers, you won't be getting the ground level information. Okay. And the other thing, like, when you scan, the PRF and dual PRF velocity ambiguities have to be considered. We have to set the parameters. Normal scan may be different, but when there is a cyclone approaching the radar, the operators there have to set different scan strategies and focus on the parameters as well as the movement of the cyclone. That is one thing. And although we take all efforts, still sometimes issues like you can say some antenna misplacement also can happen. The calibration of the radar is one important thing one has to take care. So if they are supposed to calibrate the radar every year, for the position using a sun calibration method, and also for reflectivity by using a known target, rather releasing some balloon-borne targets. That way also they can see. Okay. So, and in cyclone situation, it won't happen, but in non-cyclone circulation, if there is no cloud, you don't get be able to measure velocity. That's so I think we can go for interactive sessions, or if people like to have some questions.
Yes. So before moving to the question answer session, we can have a photo session. I request all the panelists to switch on their video and request our chief photographer, Dr. Mohan, to take a photo.
Everyone, please be ready. Devendra Pradhan, sir, please. Mr. MD Shalom.
Sagada is not there, Shalom.
Shagata Paira. If possible, please switch on your video. Okay. Ready? 3, 2, 1. Click. Thank you, everyone.
Thank you. So now I request Dr. Divya and Dr. Swagata to take over and have the QA session. Please conduct the QA session.
Thank you so much, sir. And thank you, Reddy sir, for delivering this very nice presentation. So there are some questions. So I am taking one by one. There is one question for cyclone detection radar. Which place is better to establish, from ground or satellite is better?
Cyclone detection radars are always installed on ground and the coast. And if islands are there, islands are the places, because they will be much closer, because the range of the radar is the limitation. So we have go maximum 500 kilometers or sometimes 600 kilometers only. So it has to be nearest location to the cyclone formation.
And addition to this question, how to make to work in network the Doppler radar for monitoring from one center, the range of detection, any challenges in monitoring cyclone, especially in forecasting?
Yeah, radar networking is already done by this NMC's National Meteorological Agencies, like IMD in India. So there is a central server where all the radars are connected. The data almost in near real time. So sooner the scan is over, every 10 minutes a scan is being done now. It can be at a higher frequency also if required. And the data soon after the scan is over automatically uploaded to the server. And the server would take the data from all the network radars, maybe 30 radars or 100 radars. So it will generate a composite image. Like USA, if you see the radar rainfall maps, they show radar observed rainfall maps. So this is the composite image generated using a network of radars. I think they are using 150 radars in the US system. And in India, we have, I think, 36 radars now working. They have to, in India also, if you see the website, ddgmui.mausam.imd.gov.in, under that DDGM UI. So if you go there, there is a composite image generated. They are generating South India, some 4 radars are there in that, North India, West India, East India, like that, and whole India together also. So that way the networking radar is very useful. And it will remove the ambiguities concerned to the beam height as well as some more also. Because if the radar from Chennai location is traveling, sorry, system is traveling from Chennai to say north side towards say Visakhapatnam or Machilipatnam, the nearest radar would give you the lowest beam elevation angle. So the ground coverage, closer ground coverage is better in that. And the second part of the question, I think I missed from my mind.
any challenges in monitoring cyclone, especially in forecasting?
Yeah, challenges are like when the cyclones come very close to the radar station, it is a severe weather. It has a lot of wind, lot of rain, destructive properties are there. Sometimes the radars themselves are hit by the cyclones and they get damaged. That is a big challenge. Maintaining the power is one other big challenge. Maintaining a communication is another big challenge. So if the storm is going, say, 100 kilometers away from the radar, that becomes easy, somewhat okay, manageable. But if it is really striking the same station, then it will be a hectic task to rather real challenge these two things. Manpower, you will have to sit round the clock and sit, and people cannot commute from office to home or home to office. If the system is short-lived, fine, but if it is sometimes long-lived, like 3 days, 4 days, then it would be difficult. These are the challenges.
Thank you, sir. So there is another one question from Satish. What is the importance of the shape of the eye?
Yeah, it has shape, a fully circular shape in makes an idea that the wind is very strong there, because the circular nature happens because of the strength of the wind only. If the winds are not stronger, they would maybe somewhat elliptical in shape. So that significance it has, as far as I know. Maybe I request Pradhan Sahab to add more on to that.
Thank you, Reddy ji. You are perfectly all right. Whenever the strong winds and other things are there, as you said, it is completely circular. But in case of the weaker winds, this may not be circular. It is slightly elliptical or slightly distorted. So as in your presentation, you have shown the Filene cyclone and the other one as Ogni cyclone. There you can see there was a perfect circular shape surrounded by the wall cloud region. So this is a very important thing, whoever is asked, that the shape and the size. Smaller the size of the eye of the cyclone, that is the diameter of the eye is smaller, the stronger is the cyclone, and vice versa. So thank you, Reddy ji.
Thank you, sir. So there is another question from anonymous Chandy. Please explain terms in velocity floating equation.
Pardon? Terms in a velocity equation.
Yeah.
Generally the velocity in this radar, so V max is given by PRF into lambda by 4. PRF, if you choose high PRF, it will result in higher velocity maximum, unambiguous velocity. Lambda is basically the radar technical thing, the wavelength. So for a S-band radar, it is about 10 centimeters. For say C-band radar is about 5 centimeters. If you use X-band radar, it is much less, 3 centimeters. So the S-band radar, therefore, having higher lambda, would be more suitable for cyclone detection purposes. And not only that, it has the properties of S-band frequencies have the property of less absorption. The radar signal, the power of the radar transmitter, when it is emitted into the atmosphere through the antenna, parabolic antenna, it travels straight as like a light beam, and it goes and hits a cloud particle or something. Some energy is scattered back and received to the same antenna and goes to the receiver chain, and the intensity is measured, the time taken in to and fro journey is mentioned. So we find the location, we find the intensity that way. And in this travel process, the energy of this radar signal is attenuated or absorbed a bit by the atmosphere composition, various gases, water vapor and all. And out of that, the most absorbing thing is the water vapor. So for this S-band radar, S-band frequency rather, gives a very less absorption, the minimal absorption by the water vapor. Therefore, this is most suitable, and therefore we can get range up to 500 to 600 kilometers. If you use X-band radar, you can't get more than 100 kilometers range. Firstly, because of this reason of lower lambda and more absorption by the water vapor. And secondly, due to low power.
Yes, sir. So there is one question from Shoaib. Is there a sequence, step by step, of measuring the or the measurement is based on the data that we able to obtain from the radar?
Yeah, can you repeat, sir? There was a gap
Yeah.
in.
Yeah. Is there a sequence step by step of measuring the tropical cyclone?
Yeah, step by step means same thing what we said. When there is a formation of cyclone, right from depression stage, we are attentive about the system and we keep watch of that and keep measuring various parameters. And initially thing is the formation of eye. Formation of eye, if it is there, then we call it as a cyclonic storm. Some cyclones, weaker cyclones, they don't give a clear demarked eye location. So we should keep watching for that. So first step would be to look for the center by image. Okay, and then sometimes in satellite picture you may not locate an eye, but in radar you will be able to locate, because radar scans from ground level. The radar beam is sent from ground to the cloud system at a different height, whereas the satellite imagery is taken from a very satellite at 36,000 kilometers or 8,800 kilometers, depending on the orbit nature. So that may not, especially when the eye is tilted, you can say the eye wall is tilted, satellite pictures won't give a clear demarked eye. Radar can detect that in a better way. So there are steps, I think, what we mentioned, eye parameters, all of them, eye wall parameters, spiral bands, all those things are step by step. We should make measurement and make a record of it, and then use in every sequence, every 30 minutes or 1 hour. Maybe 1 hour is good enough frequency of updating the data position.
Thank you, sir. There is another question. Can you explain about any of clutter filtering done in DWR reflectivity?
Yes. So we are using clutter filters, generally about number 1 to 15 they are called, So lower clutter filter number means it filters out low varying. Say suppose one filter number 3 I choose in data processing. So plus minus 1 meter velocity. That is, it means radially towards or radially away velocities measured in this range are filtered out. Means because they may be from stationary echoes or non-meteorological echoes. So they are not required to be present in the radar data, whereas our focus is only velocity, reflectivity, cloud, and water in the cyclonic system or any bad weather system. So that is the thing. So we have to different, and it all depends on the unambiguous velocity also. If you set the configuration to 15 meters per second and use 15 steps of radar, the highest step 15 Doppler filter number 15 will be, if you apply it, all the velocity data will, all the reflected data will be removed. It will filtered out. Any reflectivity which has a velocity of plus minus 15 meters per second will be filtered. It means it will be clear, there will not be any echo. And in the same reflectivity, if I use filter number 1, plus minus 1 meter velocities are removed. If that reflectivity spec, what we call reflectivity pixel, is removed if the velocity is less than plus minus 1 meters per second. If it is if there is a pixel which has a velocity of plus minus 3 meters per second, that will be shown, and its intensity of the reflection will be shown. Yeah.
Thank you, sir. So next question from Jagdish Prajapati. How much maximum intensity can a DWR measure?
Yeah, basically it is the natural cyclonic system, how much reflectivity it has. So practically I say 65 dBz. In terms of the dBz, 60 to 65 dBz is the most severe cyclonic storms. They, or even the hail storms, they have the reflectivity. More than that, it is not there. Yeah.
So, sir, there is one more question. Which software do you suggest to be able to extract parameters such as velocity? And if I use MATLAB, which function?
MATLAB, actually, I'm not familiar with it. It is basically the database processing system. But the radar softwares, the radar has a software system in that, like, The radar in Kolkata, Chennai, Machilipatnam, this is the Gamatronics, or you can say the Select system, Germany system. It is using a software called Rainbow. They have their brand name. Like the radar in Hyderabad, New Delhi, it is called MedStar radar. It is a Chinese made, but with US technology. That is having a software called Iris. Iris. So interactive radar information system. That is the software name itself is like that. So they have the built-in provisions to get you the data. Suppose you want data in text format, it can export to a text format. So different ways of processing are there. The MATLAB, unfortunately, I cannot answer.
So there is one question from Satish. As the center of the cyclone has the lowest pressure, the method shown to locate the center coincides with the minimum MSLP. Does the center of cyclone from the different methods shown is always the same, or does it change? If it changes, which center is analyzed?
Actually, the statement itself is a bit wrong. Always the center of the cyclonic storm is having the highest, lowest pressure. Okay, lowest pressure. The pressure from the center towards the periphery of the system will be slightly increasing. Okay. No, am I confused? Can you repeat the question?
Yes, sir. As the center of the cyclone has the lowest pressure,
Yes.
the method shown to locate the center coincide with the minimum MSLP. Does the center of cyclone from the different method shown is always the same, or does it change?
It is the same. It is the same. In visualization, there may be difference because the radar image is at a higher level. Okay, top of the cloud it is showing. So the location, if there is a tilt, it may change. If there is no tilt, it means the same.
Reddy, one more thing I want to add here.
Please, sir.
For this question, as the question is being asked for different methods. So basically in IMD, we are measuring the center of the cyclone using satellite as well as Doppler weather radar. But as it's very obvious and clear that the center of the cyclone cannot change. It will remain at the same place. Only the resolution in measurement can be slightly different because satellite is measuring from the those places which are far away. For example, stationary geostationary satellite from 36,000 kilometers and Doppler radar from few hundred kilometers. So the center of the cyclone is the best measured by the Doppler weather radar as compared with the satellite or any other. So the accuracy is the maximum in the case of the Doppler weather. Is it okay, Reddy?
It's okay, sir. Fine.
Thank you so much, sir. So there is one question from Yuvraj. Which parameters play vital role in creating extreme precipitation or landfall?
Which parameters? That is Doppler radar parameters, I mean? Reflectivity. The higher the reflectivity, higher is the rainfall rate. So rainfall rate has a direct relationship with the reflectivity. Z is equal to AR to the power of B is the equation which is used in the rainfall estimation.
So next question is, what are the uncertainty in the radar data?
Uncertainty factors are there. Some the beam height, what I said, it is a beam when it is radar pulses, when they are traveling in the atmosphere, they are subjected to atmospheric refraction and diffraction. Okay, so we actually assume a standard atmospheric condition and assume the height of the beam at 250 kilometers. I am given in my slide somewhere. At 250 kilometers, the beam height is 4.5 kilometers. That is assuming the standard atmospheric conditions. But it could vary due to some ionospheric activities or something, the refractive and diffraction status of atmosphere. The beam may bend towards ground or away from the ground, but upwards. So either super refraction or subrefraction can happen. In that case, what we show at 4.5 kilometers, if it is a subrefraction, then it would be much close to the ground, 2 kilometers only. If it is super refraction, it is close. If it's subrefraction, it may be really 6 kilometers height. So that is one uncertainty which we do not know. We always go by standard only. Okay, then another uncertainty is what do you call the rainfall, in the rainfall estimation, we take the standard sizes, drop size distribution and all. But that is practically doesn't happen. There will be mixture in especially non-dual Doppler radar, single polarization Doppler radar, especially if there is a mixture of hail and liquid precipitation, then errors are more. If it is pure liquid, then the accuracy of data is better. So that way, depending on that status of the precipitation, the type of precipitation, you can say sometimes it is hail, solid precipitation, that is sometimes it's a graupel mixture of liquid as well as solid precipitation, sometimes snowfall. All these things have different reflectivity constant because of that. So another thing is that melting layer. Melting layer means from ground we have warm atmosphere. As we go up vertically, the atmosphere is cooling down. Generally, in our latitudes, that Hyderabad, South India, around 5.5 kilometers or 5.8 kilometers, we get 0-degree isotherm. So, okay, at that level, this if the clouds are very tall, more than that height, say 7, 8, 9, 10 kilometers height. At that top level, 8 kilometers, 9 kilometers, if the water is there in the cloud, the rain actually will be in the solid form or hail form. They will be attracting another ice particles nearby, and the size of the hail increases as it falls down. But when it reaches this 0-degree isotherm and below that, wherein there are warm temperatures, it starts melting. So the surface of that ice ball will be melting, but inside it is still a solid ice. Okay, so the reflection of that one, because of the higher diameter, is very, very high. So it gives us a false information sometimes that very heavy rainfall is happening, but really it is not that. So if you really know the zero isotherm altitude and make some corrective algorithms in the precipitation estimation, you can correct it to some extent. To some extent, only not 100%. That is.
Thank you, sir. The last question is, what is the temperature of ocean surface at which cyclone is developed?
It's about 26.5 degrees centigrade sea surface temperature situation. Above that only it is conducive for development of genesis of cyclones. Below that, not.
So one question is, have you observed migratory bird trapped in eye of cyclone in Bay of Bengal cyclones? It is very...
No. Normally, in the birds trapped in the eye of the cyclone, that is the question. Birds trapping in the eye of the cyclone. No. Normally, it is not possible because once eye is there, the speed would be definitely more than, I think, 65 kilometers per hour. In that speed, wind, birds can't be there. Before that itself, when the speeds are below that, 30 kilometers per hour, 40 kilometers per hour, they will have to escape from the location.
I think there is no question. So thank you so much, sir, for giving the answer of all the questions. Thank you so much. Thanks a lot.
You're welcome. It's my pleasure, sir.
Thank you very much, Reddy sir, for the lively discussion about cyclones. And though we got many interesting questions at the end, but yeah, very nice discussion. So before moving to the vote of thanks, I request Tyagi Sab and Somesh sir and our advisory committee chairman Pradhan sir to have some remarks on the talk, and so that we...
Well, in all respect, the talk and the question answer session was superb. It really touched all aspects of the tropical cyclone being tracked by the Doppler radars and first-hand experience and the various movie loop also of cyclone must have given a good understanding and to the participants. So thank you, Reddy Saab, and look forward for your continuous participation in the Samaj activity in the future also. Thank you.
Thank you very much, sir, for your remarks.
Thank you very much, Dr. Reddy. I was just wondering because Tagi Saab has logged in as Dr. Madan Lal Shrestha, who is the Vice President from Nepal.
Yeah,
So I was wondering whether Madan Lal Shrestha.
yeah. I changed the name, but again it appeared like that.
Okay. Anyway, so great. Very interesting lecture, Dr. Reddy, and as usual, you are very good in teaching the subject for meteorology. I've seen some of your seminars earlier. So I hope that the participants must have enjoyed your lecture very much, and especially most people look for the radar images when there are cyclones, especially for the cyclones or thunderstorms. Of course, for thunderstorms, the next lecture Dr. Pradhan Saab will be delivering on thunderstorm, hailstorm, etc. But cyclone is also equally very, very interesting. I was just wondering that, like your other standard products which you operationally archive like MaxJet and the PSC, etc. Do you also archive these cloud hydrometeor profiles from the radar on a regular basis, or there is either any special effort required to derive that? This is a question for Dr. Reddy or Dr. Pradhan. Cloud hydrometeor profiles, do you archive on a regular basis, or it has to be manually derived?
No, that is a hydro profile you are saying, sir?
Hydrometeor profiles like ice or snow or grapple or hail.
Yeah. No, actually, in most of our radars, the facility is not there because they are single pole DWRs. Only Delhi, Jaipur radars, I think, and more the X-band radars which have come recently in the Himalayan region, they have this hydrometeor classification product. That product is generated there. So they are, I think, generating on a routine basis.
Yeah, because actually one of the faculty at Central University of Rajasthan has got a project on radar meteorology from the MOES, and one of the objectives of that project is derivation of the cloud microphysical parameters and of course merging of the satellite radar and rain gauge data for deriving the rainfall. And initially they are working with the Jaipur radar. Jaipur radar is of course a dual polarization C-band.
Yes,
C-band radar.
Yeah.
So
you can interact with them. They may give you some data. Or if they are not in the habit of, because they are not updating in website. Hydroclass
they are
not updating on website.
Also, I think when they contacted the people and they were told that it is not so easy, it's not straightforward. So it's difficult. Something like that. I said it's not be like that. Anyway, if required, they can contact you. I'll advise them. I hope that some of the students are attending already this lecture, because I asked them whether they are registered for this lecture.
They should actually do, sir. See, what we do in Hyderabad, the radar, we have standard products which are put on IMD headquarters website, and we have given another link in the IMD headquarters website itself for Hyderabad. So we generate additional products which are required even municipality. 25 kilometers range is not a standard product in IMD. Out of the same 250 kilometers scan, we generate image for 25 kilometers range, 100 kilometers range, and given animations also of that MaxZ. So that as per the interest, you can see like, zooming into the data level. So with less clutter and all. So if dual pole radar is having hydroclass classification product, they can generate input in their own website instead of headquarter website. Headquarter can host these products in the same server. That way, when I was in SSD, we did it for any radar as per the, sometimes these local government, they demand certain people, certain products. So they can be specific, which may not be in the common platform of the IMD.
Right. Yeah, thank you very much. In fact, I would like to also ask Mr. Shah Alam from Bangladesh Met Department. He is the in charge of the BMD radar set. Mr. Shah Alam, are you hearing us? Are you there? Yeah, can you switch on your video?
Thank you, sir.
Yeah.
I am
Yeah.
enjoy the class. Actually, I am the learner at this stage and enjoy the
I see.
class and benefited from this class. I hope I and our country, we benefited such series of class lecture. Thank you very much.
Okay. So anyway, so thank you so much once again, Reddy Saab, and then we look forward to the next lecture, 7th lecture, again by Dr. Pradhan Saab on thunderstorms and hailstorm detection by Dr. Thank you.
I would like to convey my sincere thanks to my dear friend, very close to me. We worked together for quite a long time in IMD. So his presentation was very systematic, simple in language, and nicely organized from the basics of the cyclones, the structure of the cyclones, and many other things he has explained. So my sincere thanks and gratitude to Reddy ji for joining this training session. Thank you very much on behalf of Sama and personally myself. Thank you.
Thank you, sir, for your kind remarks. To you and Someshwar Das, sir. You can be free to take any help from me if required in future also.
Thank you.
Thank you, sir. Now I request Dr. Mohan to propose the vote of thanks.
Thank you, sir. Honored guest, esteemed speaker, valued colleagues and participants. As we bring the insightful and enriching session to a close, it is my great privilege to offer a vote of thanks on behalf of the South Asian Meteorological Association, SAMA, the Advanced Center for Atmospheric Radar Research, ACARR, and the Cousin University of Science and Technology, CUSAT, India. First and foremost, I would like to extend our deepest appreciation to Professor Dr. Someshwar Das, sir, Secretary of SAMA, for his warm welcome address that perfectly set the tone for today's event. Your steadfast commitment to our association is truly admirable. A heartfelt thank you goes to Air Vice Marshal retired Professor Dr. Ajit Tyagi, sir, President of SAMA, for your inspiring opening remarks. Your vision and leadership continue to guide and elevate SAMA to a new heights. Our gratitude extends to Dr. Paulomi Chakraborty, DST Inspire Fellow and ECT member of SAMA, for introducing the speaker. Your commitment to advancing meteorological research is greatly valued. A special thanks to Sri Y.K. Reddy, sir, Scientist App and Deputy Director General of IMD, for your enlightening lecture. Your detailed explanation of Doppler Weather Radar in cyclone monitoring, estimation of eye diameter and maximum radial velocity associated with cyclone are incredibly enlightening. Your expertise and clarity in presenting complex concepts made the session both informative and enjoyable. We have gained a much deeper understanding of these radar products and their application, which will undoubtedly be valuable in our future work and studies. We deeply appreciate Dr. Swagata Paira and Dr. Deepa Prakash for moderating the Q&A session. Your efforts ensured a lively and productive discussion. A big thank you to Dr. Abhilash Shukumara Pillai, Director of ACARR and CUSAT, and Program Convener for overseeing the entire session. Your organizational skill and dedication are crucial to the event success. Lastly, I would like to thank all the participants for their active engagement and contributions. Your presence and enthusiasm make these events truly worthwhile. Once again, thank you all for making the session grand success. We look forward to your continued support and participation in future events. With sincere gratitude and warmest wishes for a wonderful day ahead. Thank you very much.
Thank you, Dr. Mohan. So I thank Dr. Mohan also for proposing the vote of thanks. And thank you all. We will meet again on July 6th for the lecture by Dr. Pradhan sir, who will be talking about the application side on the convective storms analysis and application of DWR products to study and predict the convective storms. So I think we can wind up this session. Thank you all. Thank you very much.
Thank you, sir. Thank you. Bye-bye.
Thank you, Abhilash.
Thank you, sir.
Thank you, sir.